Okay, so maybe it's time to start.
Should I start?
If you want, yeah.
Okay, well, first of all, thank you very much for inviting me. I apologize for my lack of language skills. I can only say "Здравствуйте," and that's it. The rest is in English. Let's see. So I'm going to give some definitions first. And probably all this is familiar, but I'll go. I'm going to assume I'm working in a Hausdorff space, and by a gauge or pseudometric, I mean a function such that every open epsilon neighborhood is open in the space, and it has all the properties of a metric except this one. And I'm also going to use this notation with a closed, a bracket rather than a parenthesis for the closed epsilon neighborhood. So if you have a set of gauges on a space, they are a subbasis for a topology, which is the topology determined by the gauges. And if that topology is the same as the given topology, then we will call that collection of gauges a gauge structure, and we'll call the space a gauge space. So stop me if you want to ask a question. And it follows that if you have a one element gauge structure, then that gauge is a metric, satisfies the missing condition. So there's this well-known characterization of gauge spaces. They are the same as completely regular spaces. Is that a familiar concept? Completely regular? Yeah. And or it's the same as being able to embed them in a product of intervals. So now I'm interested in when you have a group of homeomorphisms of a topological Hausdorff space, and you have a set of gauges, when can you find a set of gauges that is invariant with respect to the group? In other words, so we'll say that the group is an R isometry group, and that the set of gauges is G invariant if all of the group elements become isometries with respect to those gauges. Okay. So when can we, the question I'm going to explore is, when can we make this happen for a given group? So when it can happen, we will say that the group is isometrizable. We can make all of the elements of the group isometries if such a gauge structure exists. And if there's a single element gauge structure, in other words, a metric that makes it happen, we'll say that the group is singly isometrizable. Okay. So what question is, what properties of the group of homeomorphisms make it isometrizable? So here is a term that I'm going to introduce that fits into the theorem I proved. So I will say that the group of homeomorphisms is equiregular if given a point and a neighborhood, open neighborhood of the point, there is a smaller open neighborhood whose closure lies inside the larger neighborhood and has the following additional property. given any point of the space, that point has a neighborhood with the property that if you look at any group element and you transport that neighborhood of the point Y by the group element, if it hits the inner neighborhood of X, then it is contained in the outer neighborhood of X. So you have this sort of behavior. And then the theorem that I'm calling the isometrization theorem is that if I have a Hausdorff space and a group of homeomorphisms and the orbit space is paracompact, then isometrizable is equivalent to equiregular. So, and there's some interesting questions about why is this particular, the paracompact hypothesis there, and I have something to say about that later. But for the moment, I want to try to explain the ideas behind the proof of this. And there were other theorems like this already known, having to do with proper isometrization of the group. In other words, finding proper pseudometrics or gauges that that make the group a bunch of isometries. And so I'll connect up to what was known before. But let me move on a little. So first of all, well, there's this question about, suppose I have a metrizable space, can I find a single gauge that determines the topology on the space and is invariant with respect to the group action? And so here's what I know, that if the space, the underlying space is separable metrizable, and I have these other hypotheses, then the equiregularity condition gives me singly metrizable. In other words, there's a single metric that makes the group into isometries. And I'll sketch why that's true. So the theorem I stated earlier will give you a G-invariant gauge structure, a bunch of gauges, and I want to reduce them to a single gauge, and this is where the separable comes in. So because I have this set of gauges, this collection of neighborhoods is a subbasis. And on the other hand, since X is a separable metric, it has a countable basis. And so this subbasis then can be reduced to a countable subbasis. And then it turns out that the gauges that show up in that countable subbasis form a countable gauge structure. And then you just do some fooling around. You decapitate all those gauges. And then you get another accountable gauge structure of metrics bounded by, or of gauges bounded by 1. And then if you just do some little trick like this, you take this, you divide each of them by 2 to the minus I and take the soup. That will give you a single invariant metric on the space that determines the topology. So this is sort of standard techniques. So if the space is separable metrizable, then and the group is equiregular, then we can reduce the gauge structure to a single element. So here's the goal of why I wanted to give this talk in Moscow. I thought somebody might be able to help me answer this question. Suppose I have a non-separable metric space and a group of homeomorphisms such that the orbit space is paracompact, then does equiregularity imply that I can reduce the gauge structure to a single metric? And I don't know. I think this is false, but I couldn't come up with a counterexample. So if you know anything about these kinds of things, I welcome new information. Okay, so all right, I put it, yeah. So I sort of stated the contrapositive of this. Is there a non-separable metrizable space in a group of homeomorphisms such that the orbit space is paracompact and the group is equiregular, and every G invariant gauge structure is uncountable? That's another way of saying it. You can't reduce. So that's what I'm looking for an answer to. So I could stop the talk here. And I've achieved my objective of telling you guys what I don't know, and I could just wait for an answer. But I think instead I have to fill at least an hour, right? I should keep going. And okay, so I want to now talk about the world of proper gauges. One of the motivations for exploring this topic comes from geometric group theory, where you're given a space and a group acting on the space, and you want to know when you can make that a group of isometries. And so these kinds of theorems play a role there. And in particular, in geometric group theory, they're typically interested in proper groups, proper group actions. And so what does that mean? Well, a gauge is proper if the closure of every epsilon neighborhood is compact for finite epsilon. And that makes the space locally compact. And a gauge structure is proper if each of its elements is proper. And a gauge space is proper if it has is proper if it has a proper gauge structure. So now, again, assume we have a group of homeomorphisms, we will say that the group is properly isometrizable if it has a G invariant, if the space has a G invariant gauge structure. And again, we could talk about being singly properly isometrizable. And again, what properties make a group properly isometrizable? So I'm going to introduce a property of the group. Well, it's of the way the group acts on the space. We'll say that the action is nearly proper if given two compact sets of the space. If you look at all of the images under the group of one of the sets that intersect the other set, if that has compact closure. So here's a little illustration. I have A and I look at all of its images under the group, and that union should have compact closure. That's what the group action being nearly proper means. And so then you can prove a proper isometrization theorem, which says that suppose your space is locally compact and sigma compact, and you have a group of homeomorphisms, then being properly isometrizable is equivalent to being equiregular and nearly proper. Now you may notice that condition that the orbit space be paracompact has disappeared, but it's in there. It's just that the hypothesis implies that the orbit space is paracompact. So, but yeah, so this this is a little bit of this is a sort of a corollary to the previous theorem if you have the right information in hand. Okay, and then a corollary of that is that if you start with a metrizable space rather than a Hausdorff space and ask this, you get the same theorem with a single gauge structure. And the proof, I think I put it in here, but I'm going to skip it. Well, no, I'm not going to skip it. I'm going to include it. So I know that on the one hand, from my previous theorem, I get a G invariant gauge structure. And I should say the two theorems that I just stated give me, on the one hand, a G invariant gauge structure, and I'm sorry. They give me a G invariant metric because this space is separable metric. And they also give me a single proper gauge. I don't know that it generates the entire topology, but if I put the two together, I do get a single G invariant proper metric on the space. So anyway, and the reason that's possible is when you take the max of two gauges, this equation here tells you how their neighborhoods behave. And so if one of them is fine, if from one of these you're getting enough open sets to generate the topology, and if the other one has compact closure, then you get the max is going to have both properties. Anyway, okay, so let me discuss briefly what was already known before this work. So I have to define one more term. G, suppose I have a group of homeomorphisms, and I give that group the compact open topology. Then G acts properly on X if whenever you take two compact sets and you look at all the elements of the group that that make one of the sets intersect the other, then that is compact in the group. So this is a condition that you need to impose a topology on G to state this condition. And my previous conditions, equiregularity and nearly compact, did not require you to consider a topology on G. They were really statements about how G acts on the space, not about the topology on G. Anyway, if you make this definition, then you can state this theorem of Abel, Manousis, and Noskov from 2011. If you're in a locally compact, sigma compact Hausdorff space, and you have a group of homeomorphisms, and they satisfy this properness condition stated above, then G is properly isometrizable. So that was, I read that paper and it was influential in the things I came up with. So it helped me. And that paper generalized a paper by Antonian and to name it, and that came earlier. And so those are the sort of precursors of what I've done. But I think the main there's a difference in emphasis where in this theorem, you needed to put a topology on G, and then your hypothesis included a condition on the topology. The theorems I proved is you look at the way G acts on space, and those are the hypotheses of those theorems, my theorems. Okay, and then just to show you that there's a difference, a very simple example, if you consider rational translations of the real line, so that's a group of homeomorphisms, then that group is equiregular and nearly proper. but it doesn't satisfy the properness condition in the theory of Abel, Manousis, and Noskov. So there's something new in what I did. So now, oh yeah, the inspiration for this work came from a question that was asked to me by my colleague, Craig Gilbo. And so let me try to explain what that is. It's a question I still don't know how to answer, but it needs the notion of a geodesic. So suppose you have a metric on a space, then a geodesic is simply a distance preserving path. And a metric is a geodesic metric if every pair of points can be joined by a geodesic. So, if you think about the circle in the plane, the metric inherited from the plane is not a geodesic metric because, the distances are too short. But if you take the arc length metric in the circle, that is a geodesic metric. And there's a well-known theorem by Bing and Moise that says, that implies, this is a correlate to it, that if you take a locally compact, locally connected metrizable space, then it has a proper geodesic metric. And so Gilbo's question was, suppose that I have such a space and I have a group of homeomorphisms, and if the group acts properly, or you can replace that by nearly properly and equiregular, well, in any of those situations, can you find a proper geodesic metric? So you want your metric to have this property that distances are realized by geodesics. And I don't know the answer to that. And that was the inspiration for this work. Okay. And it turns out that what I was able to prove that hadn't been proved before relies on a lemma. And I want to tell you what that lemma says. So a G, say you have a group of homeomorphisms, I'll say it satisfies the star refinement condition if every G invariant open cover of your space, in other words, open covers that are closed under the action of G, if every G invariant open cover is star refined by a G invariant open cover. Okay, so I gave that condition a name, star refinement condition. And then the lemma that makes these things possible is this, that if your group is equiregular, then the orbit space being paracompact is equivalent to G satisfying the star refinement condition. So this explains where that hypothesis that the orbit space being paracompact comes from. It's basically equivalent to this other condition, and that other condition is what enables me to construct these G invariant gauges. So it turns out, and one way of interpreting this is, if I want to prove the theorem by the method I know, I've got to assume paracompactness. It's necessary and sufficient. And that's about all I can say about this paracompactness condition, except that, there's probably a better theorem out there, but I don't know how to prove it. Let's see, what else? Oh, yeah, let's see. So all of this stuff is old. In some sense, these theorems could have been proved in the 1950s when people like A.H. Stone, who invented the notion of paracompactness, and Ernest Michael did their work, but they weren't. So I'm talking to you today. Okay, so let's see, what time is it? So I want to explain where the ideas behind the proof come from. And they really come from these techniques developed in the 1920s by Alexandrov and Urisin, which I assume is part of your education. Those of you in Moscow, I don't know what they teach anymore, but they were part. What?
Before you go into the proof, I have one question.
Yes.
If your group G is compact, then are those conditions automatically satisfied?
Let's see. Well, yeah, I think so. I mean, the condition, the proper action is saying that certain subsets of the group are compact. These things, and I believe they're closed. So I think the answer is yes, but I'd have to think about it a little more. Okay.
Okay, so I've seen it in some paper by Antonian that for compact groups, so there was a certain theorem by Pelé about G invariant metrics for actions by compact and locally compact groups.
Right.
So that should also follow from your results, right?
Yes. Yeah. Well, I think those they may have followed from the results of Abel, Manousis, and
I see.
Moscow.
Okay.
So I didn't bother to list all of those, but I think you're right. Yeah, that they were, as I said, they were taking the point of view of imposing conditions on the topology of the group, and I was trying to stay away from that. But I think you're right. Yeah. So I would have to look back at their papers. I'm not sure. Okay, let's see. So I wanted to talk about this old technique from the 1920s of Alexandrov and Urisin. Let's see. So, wait, I went backwards. So I need a kind of more general notion than a gauge. Suppose you have something that has all the properties of a gauge, but it takes on the value infinity as well. Then I'll call it an infinity gauge. And you can consider sets of infinity gauges. They will determine a topology because they determine a subbasis for a topology. And you can say two sets of infinity gauges are equivalent if they determine the same topology. And you can say, well, a Hausdorff space whose topology is determined by a set of gauges is a gauge space, an infinity gauge space. So I want to allow the possibility that the gauges take on the value of infinity. And if they do, and you look at the subsets of the epsilon neighborhoods where epsilon is equal to infinity, then you get things I'm calling crevasses. Here's a schematic picture of what I'm thinking about. The space is divided up into these open sets that are infinity neighborhood points. Come up in a minute or two. And I need a little more.
I'm sorry.
Yeah.
Rick, I can't hear you. And also,
You hear me now?
I can't hear you. Okay, now it's better.
I'll move my head.
Could you comment on this picture? What does it stand for?
Yes, so I'm thinking of the infinity neighborhoods at various points. So you think,
Well, I'm sorry. Again, I can't hear you.
I don't know what the issue
Yeah.
is.
Yeah, Rick, can you hear me, Rick?
I hear you.
Bob
Yeah.
Edwards here. Yeah, okay, Rick. Yeah, all throughout the talk, there's been an audio problem, and it's not clear where it resides. What I'm talking, there's been a feedback issue, but now in the last minute, there's been a more serious audio problem, which sounds like something's rubbing on the microphone or somewhere between your mouth and audio feed. It's
Oh,
just
really?
not working.
I'm trying to, I don't know what that would be.
Okay, now you're speaking very clearly. I wonder what the issue is.
Okay. I've been using an iPad that's wired to my computer, and I'm going to go. Okay. How is it now?
That's been perfect for the last 5 seconds. Perfect.
Okay. Well, stop me if.
We'll keep you informed. We'll keep you informed.
Okay. So I'm sorry, but so what this picture?
Oh, now,
I'm sorry.
now
Go
there
ahead.
it is again. I'm sorry, Rick. There was just a little bit again of the feedback issue in the last 5 seconds,
Okay.
and I wonder what's going on.
Well, now is this causing it?
I don't hear anything right now.
Okay, I'm not sure what the problem is, but anyway, let me proceed and stop me if there's an issue. So what this picture means to me is that at the bottom of these sort of parabolas, that's a point, and you're looking sort of at the graph of the distance function, and the space is divided into these regions that represent the infinity neighborhoods of different points. So I'm looking at really the graph of the distance function here. Does that make sense?
So, are you looking at some finite collection of points, or maybe countable collection?
It might be uncountable. You know, it depends on the space. It could be an uncountable collection of points which are all distance infinity from each other, and you're looking at their epsilon neighborhoods or their infinity neighborhoods. So if a space has one of these infinity gauges on it, and then you can ask what are the infinity neighborhoods of different points, and it will divide the space up into a bunch of open sets. And this is just a schematic picture of all that. I wouldn't worry too much about the picture. It's just a way of visualizing things. Okay, so, and then I need some terminology. If I have two open covers and I have a sequence of open sets that successively intersect each other, kind of like this. I'll call that a chain of length. Well, this would be a chain of length 4, okay? And oops, what's wrong way? And then if 2 points are joined by a finite chain, I'll use this notation. And if I look at a point, everything that can be joined to it by a finite chain with respect to this cover U is called a U component. And the space is U connected if all points can be joined by chains. And I'll use this notation U of XY for the chains joining X to Y. It could be empty. And then here's an important notion. An open cover V, K refines an open cover U if every chain of length K in V is contained in a single element of U. So 3 refined would be something like this. I got a chain of length 3 in V, and it would be contained in an open set mu. And then, of course, you're familiar with the star of a set with respect to an open cover is the union of the elements of the open cover that hit the set. And then the notion that one cover star refines another is that the stars in V refine U. And then there's this notion, I don't know where this terminology came from, but it was certainly implicit in the work of Alexandrov and Urisohn, but I know it was in the work of R.L. Moore. He talked about a development. A development is a collection of open covers where the stars, with respect to points, form a basis for some topology. Maybe not the given topology, but those would form a basis for a smaller topology. Okay, and we call the topology determined by that basis. The topology, well, it's the topology determined by the basis, and I'm going to actually be considering not just a single development, but a whole bunch of developments, and then the stars of those open covers in those developments will be the sub-basis for a topology, which is the topology determined by the collection of developments. Sorry, this is getting technical, but so if I have a development, I will call it a K development if successive covers K refine their predecessors. In other words, chains of length K from the nth plus first element are subsets of element of the sets in the kth element. It's too many words for me to say, but and there's also the notion of a star development where UN plus 1 star refines UN. Okay, and then turns out it's easy to see that if you have a star development, it is also a 2 development. In other words, star refining implies 2 refining. And if you have a 2 development, in other words, 2 refining, and you skip every other stage, you get a 4 development. And that in turn is a 3 development. So it turns out that the number 3 is important here. That's why I stated, I make a point of it. And so, for example, if you have an infinity gauge, something that takes on the value of infinity, and you look at the neighborhoods of radius 2 to the minus n, they are a star development of the topology. Okay, so now Alexandrov and Urisohn proposed a method for defining, we're looking at it from the modern perspective. They came up with a method of defining infinity gauges. And so if I have a 3 development, you can associate an infinity gauge with it. And I had to give it a name, so I called it the AU infinity gauge associated with this development. And let's see. And it has this property that if you look at the 2 to the epsilon neighborhoods with respect to the gauge, the AU gauge, infinity gauge, they are nested in the stars with respect to the development in the way specified here. So what this is telling me that the topology determined by the development is the same as the topology determined by the gauge, for example. Yeah, so in fact, that's what this says. So Alexandrov and Urisohn come up with this method of defining an infinity gauge from a development. And it has this property, which means that the topology, the development and the gauge give you the same topology, and the what I call the crevasses for this infinity gauge correspond to the components with respect to the U1, the first element of the development. If you can chain 2 points using U1, they're in the same, they're a finite distance apart with respect to the gauges, and that's if and only if. Okay. And to proving this relationship between the neighborhoods with respect to the gauge and the stars is where you need 3 developments. And this is, I don't know, this is something when I was a grad student, I think I became aware of this theorem. Anyway, so, well, how did yeah.
So I guess if you replace 3 development by a strong star refinement, that should also work. But
yeah, right. 3 development is weaker than 4 development. Yeah, or star refinement. Yeah, you would get a similar. You might. Let's see. Star refinement gives you 2 developments, and then you have to skip every other term in the development to get.
Yeah. I was thinking about strong star refinements, which is that you take.
Oh yeah.
Star,
okay. Right.
The
That's
star
where
of a set, not the star of a point, but the star of a set from the.
Yes. Yeah, you're exactly right. That would give you a 3 development on the nose. Right. Okay. So so what's the idea behind their proof? Well, I sketched it here. You take all the union of all these open sets or covers in the development, and you assign a diameter to each one of them, which is, it could even be 0, but use this function. So the higher index the open set comes from, the smaller it is. And then you look at chains in this cover of different sized elements, and you add up their diameters, and you get a length function on chains. And then you just take the inf over lengths joining 2 points to get what I'd call the infinity gauge, the Alexandrov-Ursin infinity gauge. But you have to put infinity in there because it might be the case that 2 points aren't joined by a chain, and then you assign them distance infinity, and then that's why this function, this gauge is really an infinity gauge. Sometimes you get infinity out of it. Okay. And then this condition follows, and you get these other properties that I mentioned. You get the same topology from the gauge as you get from the development, and the row crevasses are the same as the U1 components. And now there are a couple of ways you can get rid of infinity. One is if the whole space is U1 connected, then this gauge will be finite valued. And of course you can do that by throwing the whole space in to the development. So you can connectify things. And the other thing is you can decapitate them. You can replace the gauge you get from this Alexandrov-Ursin technique by one that's cut off at the value 1. And so that gives you this classical Alexandrov-Ursin metrization theorem. That if you have a Hausdorff space whose topology is determined by a 2 development even, then it's metrizable. Remember, 2 developments, you can turn them into 4 developments by skipping every other element of the development. And so you get, this was their 1923 theorem. And then more generally, if you have a collection of three developments in a Hausdorff space, such that the topology is determined not by a single development, but by all of them together, then you get a gauge structure. You may not get a single gauge that gives you the topology, but you get a collection that does. And here's the problem with this, is that if you're trying to create a proper gauge structure, these techniques I mentioned up here of making the gauge finite don't work. They create non-properness. If your space is not compact, they're going to make your gauges non-proper when you decapitate or when you do this connectifying process. Okay. So in order to get proper metrics, you've got to add some technique. But I want to, before I turn to the question of how you get proper metrics, I was going to say something about all the metrization theorems I'm aware of, sort of a general comment. Now, Sergey, can you tell me, when should I stop? I have to.
You can continue at least for 2 hours, and then.
Then okay. We'll, I think I'm safe. I'll probably run out of things to say before 2 hours. So, yeah. Okay. Anyway, you have a lot more patience there than we do in Milwaukee. But okay, so I want to make some remarks about the metrization theorems I'm aware of. Well, the one I was just talking about, the Alexandrov-Urisohn theorem, I might characterize the proof as set theoretic. You build the function using properties of the sets. But then there's this Urisohn metrization theorem that I put a question mark by the date because I wasn't exactly sure when it was proved. This is about when Urisohn died, I think, in 1924. But anyway, so the method that at least the proof I've seen is what I would call geometric. You embed the space in a space you know is a metric space, in this case in the Hilbert cube. And if you look at the more general metrization theorems like Nagata, Smirnov, the proof is geometric. You embed the space in a countable product of metric vector spaces, or Bing's theorem, where you embed the space in a countable product of what were called hedgehogs. When I was in grad school, a hedgehog is the metric cone over a discrete space. And then I have a preference for geometric proofs. That's just my nature. But if you look at the proof of the Bing-Moise convex metrization theorem, which I mentioned earlier, this is the one that gives you geodesic metrics. It really applies to piano continua, so compact, connected, locally connected metrizable spaces. And they prove that these spaces have geodesic metrics. And I had never looked at this proof until maybe a decade ago, and I looked at it, and it's fiercely complicated and set theoretic, and not what I would call geometric. And so here's a problem I'm throwing out there: is find a geometric proof of this theorem. And I mean, I think it would be helpful. And here's a more precise way of formulating this. Suppose that you have an embedding of the piano continuum, which you want to, for which you want to construct this geodesic metric. Suppose you have an embedding in a Hilbert space, prove it can be approximated by embeddings with this property, that the minimum length wait, what does this say? Yeah, oh yeah, so that you can use the length function within the image to construct to give a geodesic metric. So you want to, in other words, you want to take an arbitrary embedding in a Hilbert space and perturb it so that nearby points are joined by paths of finite length, of small length. If you could do that, you would have what I would call a geometric proof of this Bing-Moïse theorem. And I've thought about this. I have some ideas, but I don't know how to finish it off. That would satisfy me. I'd like to know what the answer to this is. Okay. Let's see. I think I'm about done. Yeah. So now, how do you make these infinity gauges into proper finite valued gauges? That's the next question. And here I've sort of taken ideas that show up in this paper of Abel, Manousis, and Noskov, and I've modified them. So I can't claim a lot of originality here, but I think I can give a clearer picture than they did, but that's about it. Oh wait, I went backwards, sorry. Okay, so here's what I call a preview. If, suppose I want to construct proper gauges on a space. Well, I can start off using that Alexandrov-Ursin method to get infinity gauges, but I could make these gauges finite value by using these techniques, but that might destroy properness. If properness were something that I could hope to achieve, I might mess it up by this method. But you can introduce what I've called bad tunnel systems, and that will allow you to gain properness. So let me explain the idea. So suppose I have an infinite value gauge, and I form the collection of points that are in the same crevasse. So they are a finite distance apart. Look at all such unordered pairs. And then I want to define what I call a tunnel system for the set of crevasses. So first of all, it's pairs of points. It's a set of pairs of points that belong to different crevasses. So the distance between these points is infinity with respect to rho. And furthermore, if I take any 2 points in the space, I can join them by a sequence of points where 2 points either are in the same crevasse or they are elements of this collection T. So I'm assuming T is big enough so I can get between any 2 points of the space by a sequence of steps where either the 2 points are finite distance apart or I'm an element of T. And then I also need a length function for these steps that go between crevasses, the elements of T. And the only condition on that length function is that the inf of all the values is strictly positive. And I'm going to call the elements of T tunnels. And there was a notion in this Abel, Manousis, Noskov paper of bridges. So this is I stole it and renamed it. And so here's a schematic diagram. I have an infinity gauge. It gives me a set of these rho crevasses, and then I connect them up with tunnels, and I assign a length to every tunnel. Okay. And then suppose I've done this. I have this tunnel system, and I look at the set of sequences where every step is either pair of points that are finite distance apart or in the tunnel system. And I will define a function, sort of a distance function now associated with this setup. And so I define a length to this system, and it's the sum of the lengths of the steps, where a step is either the distance between 2 points if the distance is finite, or it's this lambda of the length of the tunnel. So I'm defining a function that way. And if I then take 2 points, I look at all of the sequences of this script in script S that join the 2 points, then I define a gauge associated with the original infinity gauge in the tunnel system by just looking at infs of path lengths, basically. So I just look at all the ways, the inf of all the ways of getting from X to Y by either going through tunnels or going between points that are a finite distance apart. And then I'm calling the results a gauge associated with the original infinity gauge in the tunnel system. And then it's not hard to prove that if you start with an infinity gauge in a tunnel system, you end up with a finite value gauge. And that finite value gauge gives you the same topology as the original infinity gauge. And then how do you make that gauge proper? That's the challenge. So any questions? No. Okay, and so the idea is this, that we'll call an open cover proper if when you start with a compact set and you take the star of the compact set, that has compact closure. And then a development is proper if each element in the development is proper. And an infinity gauge is proper. Well, it's the same definition as for a gauge. You want the epsilon neighborhoods to have compact closure where epsilon is finite. And then an infinity gauge structure on a space is proper if every element of the infinity if every such infinity gauge is proper. And again, a space has a proper gauge structure if you have such a proper, well, if the space has an improper infinity gauge structure, we call it a proper infinity gauge space. So I have modified the notion of proper gauge space to proper infinity gauge spaces. But here's the theorem. Suppose that you start with a proper 3 development. So where all the stars of compact sets have compact closure, and then the associated infinity gauge is proper. And then you would hopefully, if then you created a tunnel system and you got the associated finite value gauges, it would be proper. Well, that may or may not happen. It depends on the tunnel system. And so a tunnel system is proper if it satisfies this condition, that whenever you take a compact set and you look at all the elements that are connected to this compact set by tunnels and have length function less than epsilon, that has compact closure. So that's a mouthful, but it turns out that's the necessary condition, so that if you have a proper infinity gauge structure and a proper tunnel system as just defined, then this gauge you get out of it is proper. So we now have a technique for coming up with proper finite value gauges. You start out with a proper 3 development that gives you a proper infinity gauge. Then you devise a proper tunnel system, and then the associated gauge will be proper. And so that's what we've got to do to come up with proper gauges. And okay, so now I had introduced this notion before. What is a bad tunnel system? Well, a bad tunnel system is one where the number, or if you look at the set of elements of the tunnel that are distance less than epsilon, that's a finite set. So this is a pretty restrictive condition. And the reason I've called it a bad tunnel system is it's very inefficient. If you wanted to get between 2 points, you might have to go a long distance. You're looking at steps that either are in your tunnel or finite distance apart. Because of this, only finitely many tunnels have length less than epsilon. This might take you a long time. And so I'm calling that a bad tunnel system, but bad is good because if your tunnel system is bad, it's proper. So the idea is if you can find bad tunnel systems, then you're going to be able to create proper finite value gauges. And so it turns out that if your space is sigma compact and you have an infinity gauge, then the set of crevasses is countable. I wrote down a proof, but it's fairly straightforward. If you break your space up into compacta, and the number of crevasses that can hit a given compactum is finite because it forms an open cover of the compactum, and then the set of all crevasses is just the union of these finite sets, so it's countable. And now I want to describe a specific tunnel system, assuming that I have countably many crevasses, which is what I will have if the space is sigma compact. And the idea is this: the number of crevasses is countable, so you label them, and then you choose points out of each, and then you connect up you create tunnels in the way I've shown, where you only connect everything to the point x0. So it's very inefficient to get, say, from here to here, you've got to go back to x0. You got to go all the way back to the beginning. And so that's why I call it a bad tunnel system. And then you simply define the length of the tunnel that goes from x0 to xi to be length I. And I call this the hub tunnel system because everything goes through the hub at x0. And this is bad. There are only finitely many tunnels of length less than a given epsilon. And because it's bad, it's a proper tunnel system. And so the corollary is that if you are in a sigma compact space and you have a proper 3 development, then you apply all these ideas. You use the 3 development to get an infinity gauge, and then you take this bad tunnel system, and that allows you to come up with a proper finite value gauge that determines the topology. Okay. Well, I sketched what I just said. You have your proper 3 development. From it, you create the infinite value gauge. That will be proper. You take a bad tunnel system, it's proper. And that gives you, when you use both the tunnel system and the original infinity gauge to define the distance between 2 points, you end up with a proper finite value gauge. and that gauge determines the same topology as the original development. Now, here's a virtue of properness, which makes it easy to propagate. So in other words, if I had I start out with one proper 3 development, and I use the technique just described to come up with a proper gauge, but suppose that development alone does not determine the topology on the space. I need to consider other developments. Well, that's not a problem, as it turns out, and this explains why. Suppose I have a gauge structure and I have a single infinite proper gauge. Well, then if I replace the gauge structure R by the maximum, all the gauges of the form max R sigma, where sigma is proper, that's also a proper gauge structure. So I can assume everything is proper if one gauge is proper, I can make all of them proper. So this is a kind of helpful observation. So I get this corollary of X is a sigma compact Hausdorff space, and I have a collection of 3 developments that determine its topology, and I also have one proper development. All I need is one. Then using the technique I described and this contagiousness property, I get that X has a proper gauge structure. So so things fit together fairly conveniently. And now finally, the last step, really, I don't think I'm going to make 2 hours, but the last step is I really want to make everything G invariant for some group of homeomorphisms G. So I want to take the techniques I've just described and make them respect a group of homeomorphisms. Well, it's not difficult, but there's one step which is hard, but it was hard for me. Okay, suppose we have a group of homeomorphisms. Here some standard notation. G times A is the union of all the images of A under elements of the group. And so an open cover is G invariant if the open cover is closed under transformation by group elements. And the development is G invariant, or sequence, development is G invariant if each open cover is G invariant. And then there's some obvious things you can say. Suppose I have a G invariant open or development, and I form the Alexandrov-Urison infinity gauge, then both it and its decapitation are G invariant. And that's straightforward. And again, if I have a collection of G invariant developments in a Hausdorff space that determines the topology, then that makes the group isometrizable, because I simply take these Alexandrov-Urison infinity gauges and decapitate them, and I get a G invariant gauge structure on my space. Here again, I'm not worried about properness at this point, so I don't have to worry about tunnels and things like that yet. Now, what does it mean for a tunnel system to be G invariant? Well, that means that the tunnels are G invariant. In other words, whenever you have an element of the tunnel system, of the tunnel, you can move it by G and you'll remain in the tunnel. So the tunnels are invariant under the group action, and also the this length function is invariant under the group action. So that's obvious definition of what it means for tunnel system to be G invariant. And then the appropriate lemma here is that if I have a G, if I come up with a G invariant infinity gauge and I have a G invariant tunnel system, then, and I create this finite value gauge from them, it will also be G invariant. And this is, again, straightforward. So I have a way of making things G invariant if I can make my open covers in the developments G invariant, and if I can make the tunnel system G invariant, then I'll get a G invariant gauge. And so now suppose I don't have a G invariant tunnel system. There's a way of creating one, which is fairly straightforward. First of all, I want to enlarge the tunnels to contain all of their images under group elements. So I've called that script GT or G script T, and then I have to know how to define a length function on this enlarged set of tunnels, and you just take infs over is this correct? Oh yeah, you know, if you take an arbitrary pair of points that are in this enlarged tunnel system, large set of tunnels, you can always translate it back into the original set, and you don't know that the length function is invariant under that procedure, so you take infs, and that works. The requirements on lambda are pretty minimal, just that the inf of all of the possible values is positive. And so this works. And then the point is that if I've started with an arbitrary tunnel system, this process will give me a G invariant tunnel system. So, yeah, the question going back here though, the question is if everything up to this point was proper and I create this enlarged tunnel system, how do I know it's proper? And so that I have to face that issue and recall that what nearly proper meant, it was back on an early slide. It meant the group is nearly proper if when you take two compacta and you look at all the union of all the images of one compactum under the group that hit the other one, that set has compact closure. That's what nearly proper meant. And so if the point here is that if my group X is nearly proper and I have an infinity gauge and I have a bad tunnel system, then this enlarged tunnel system will be proper. So, you know, this is not hard to prove. It's fortuitous that we can prove it. And so the corollary is that if you start with a sigma compact space and a group of homeomorphisms that's nearly proper and a proper development, and you form a bad tunnel system, which you can do because you're in a sigma compact space where the set of row crevasses is countable, and you create the bad tunnel system and then you enlarge it to make it G invariant, then and use that enlarged G invariant tunnel system together with the proper infinity gauge that you got from the Alexandrov-Urison method. Then you you get a single value, you get a proper gauge on the whole space. So in other words, this is telling me how I can get proper gauges. If I'm in the, if my group is nearly proper. Okay. So suppose now that I'm in a sigma compact space and my group, I have this nearly proper group and I have a collection of G invariant 3 developments that determine the topology, and I have a G invariant proper development, then my space is properly isometrizable. And this is where I would use this contagiousness property to make everything proper. Okay. So wait, I wanted to go back. I'm going forward. Hold on a minute. So at this point, I'm almost done, except I have to know how to create G invariant 3 developments. If I can do that, and I can and proper a single proper 3 development G invariant, then this corollary is telling me I can properly isometrize the group. I can create, in other words, I can create proper gauge, a set of proper gauges that form a gauge structure. They determine the given topology, and they make all the elements of the group isometries. So now I wanted to recall this notion of a group having the star refinement condition, which means that given a G invariant open cover, you can star refine it by a G invariant open cover. This is, if I can do this, if the group has this property, then I know I can carry out this process that I've been building up. Because this allows me to create G invariant developments. So here's what I call the key lemma. If my group is equiregular, and then I know that the condition that the orbit space be paracompact is equivalent to the group having this star refinement condition. In other words, I can take a G invariant open cover and find a star refinement that's G invariant. And actually, I guess this is realizing that this was true was sort of the motivation for all this work. This is the lemma. And so let me just briefly describe, maybe you can see it already. Why is this the key? So I don't know whether I'll actually sketch the proof. Anybody who really wants to see the proof, it's not edifying to see the proof. It's highly technical, but
so we have signed up for another night.
Yeah. She wasn't sure, but she was pretty sure that you guys were staying another night.
Yeah.
Do you guys need anything?
No, just, is there an ice machine? How
Hey,
does one
Bob.
get ice around here?
Bob, turn off your audio.
Yeah. Oh, sorry, Rick.
Okay.
Just
Okay. Hi, Judy. Anyway, this key lemma lets you accomplish everything I wanted to. And for example, this lemma B says this, that if I have an equiregular group and the orbit space is paracompact, then I can construct a collection of G invariant developments that determine the given topology. And it's fairly what I want to do, but I think I wrote down the proof. Yeah. So how do you do this? You start out, you take a point and an open set containing it. And since G is equiregular, then that meant I can find a smaller open set containing the point whose closure is in the bigger open set. And I have all of these neighborhoods at every other point, which if they translate via group elements to hit the closure of V, then they are contained in the larger open set. Okay, and I simply form the open cover of all images of these neighborhoods of points, and this is a G invariant open cover. And then let me go back. The key lemma allows me to star refine this first open cover. I call that V. Yeah, okay, I'm just, sorry. So this first cover has this property, it's G invariant, and the star of the point with respect to that open cover is contained in U. And then I apply this key lemma to create a sequence of star refinements of these open covers. And they form they form a star development, which if I then skip every other element, I get a 3 development. And the star of the first element of the development at the point X is contained in the open set U. And so if I do this for every point and open set that contains it, I'll get a collection of G invariant 3 developments that determine the given topology. So that's what the lemma said exists. So in other words, this tells me how to get these G invariant 3 developments that I need, and then I can prove the isometrization theorem. You know, assuming, well, let's see, I think I sketched the more interesting direction of the proof. The opposite direction is straightforward. But let's see. So if I assume the group is equiregular, then it suffices to find a collection of G invariant 3 developments that determine the topology, because then you use the Alexandrov-Urison technique to get infinity gauges, which you can then decapitate to get a gauge structure, and G invariant gauge structure. So, but the point is that the lemma I just stated and proved gives me such a collection. So this is fairly straightforward, given the key lemma. And then if you want to create proper you want to create proper gauge structures that are G invariant. You need a few observations about the locally compact, sigma compact situation where you have a group of homeomorphisms. And I would say these things like this were known, and I wrote down a couple of lemmas that say all the things you need to say about this situation. Let's see. Well, I say I proved it a little bit. Let me go back. So what this one says is, suppose I'm in a locally compact, sigma compact Hausdorff space. This is the situation where it makes sense to ask for G invariant proper gauge structures. And suppose that the orbit space is regular, and that's enough in this situation to, well, you get from that the orbit space is paracompact. And so that part of the whole thing is going to fall out. And then what this says is you can find a sequence of closed sets in the orbit space of compact sets in the orbit space. The problem is the orbit space may not be Hausdorff. So, and in fact, you want to be able to deal with space, group actions where the orbit space is not Hausdorff. It's common occurrence. And so you got to worry about what happens when that orbit space is screws up. It may not be T1. Then nonetheless, you can take the orbit space and represent it as an ascending sequence of closed compact sets. And then that tells you that the orbit space is locally compact, sigma compact, and paracompact. So in other words, I get that paracompactness hypothesis out of this. And there's a second lemma that says that if you add that the group is acting nearly properly on the space and G mod X is regular, then you have a G invariant proper open cover. So recall that to get started on creating a proper gauge structure, you need a single G invariant proper open cover. If you can get that, then you can use these techniques that I've already described, including that contagion technique, to get a proper gauge structure. Oh, went the wrong way. I got this, I'm using this iPad and I haven't quite mastered it yet, but I got a right swipe advance, goes back to the previous slide, a left swipe goes to the next one. Okay, so anyway, given those lemmas, you can prove this proper isometrization theorem, which says that if you're in a locally compact, sigma compact space and you have a group of homeomorphisms, then in that situation, being properly isometrizable is equivalent to being equiregular and nearly proper. And well, I sketched this proof, but if you assume in the hard direction, if you assume the group is equiregular and nearly proper, again, it suffices to find a proper, wait, what have I got? Oh, you have to do the thing you did in the non-proper case, namely find the G invariant 3 developments, and that will follow as it did before. And then you need a single proper 3 development. And then, well, lemma C tells you that the orbit space is paracompact, which is the condition you needed to create the non-proper collection of developments. And so that's what this is saying, that once you get the orbit space paracompact, you're in a situation to carry out the previous proof idea. And then lemma D gives you a G invariant proper open cover. And then you again use that lemma, that key lemma, to star refine it. And that gives you a bunch of proper open covers. And so you get a proper 3 development. And once you have that plus the non-proper developments, you use the contagion principle to create a collection of proper developments that give you the topology. So that's the idea. Now, I probably have said enough. The details of the proof, I've written them in the slides, but going through those proofs, I think is probably will lose a lot of people. I just don't know. At this point, I would skip over those proofs. I had some other remarks that I would like to say, unless somebody has an appetite for watching proofs. Oh, let me say one thing though about, so the lemma A is the key here. Wait, where am I here? Yeah, this is the key, that that the orbit space being paracompact is equivalent to finding these G invariant star refinements. Once you can do that, everything else works as I've described. And I sketched the proof, but I'm just going to go through it and get to the end of it, because I made a remark there. It takes like 3 slides to get through this whole thing, which, yeah, here's the remark, that this is inspired by a proof of Stone, so that a paracompact regular space, every open cover is star refined by an open cover. That you combine Stone's proof with a group of homeomorphisms, and you can modify Stone's proof to prove this lemma A. Stone's proof is, tricky, and so I don't know. This lemma A didn't occur to me for a while, but then eventually I was able to squeeze it out of Stone's proof. The other lemmas that I mentioned, there's C and D. These are applied to the locally compact, sigma compact case. They're sort of fun. And I think trying to read the paper of Abel, Manousis, and Noskov inspired me to work out the details of these proofs, because the stuff that I needed was sort of buried in the literature, like Sergei mentioned work of Palais and all. It's in there, but trying to pry it out seemed more painful than just writing down proofs. And so I put proofs of these other lemmas that apply to the lowly compact and sigma compact cases in the notes if anybody wants to read them. But yeah. Anyway, let me go past them, and because there's one more remark I want to make. Earlier I don't know if you recall it anymore. I'm sorry, flashing through all this stuff. Get past the proofs of these lemmas, and I'm willing to send these slides to anybody who wants to look at it. Okay, earlier I mentioned a problem which I'm interested in knowing the answer to, which is that suppose that I have an equiregular group of homeomorphisms and acting on a metrizable space. Can I, in that situation, find a single metric that makes those into isometries? In other words, can I find a single G invariant metric? I know I can find a G invariant gauge structure, but I don't know that I can boil it down to a single metric. And as I said, the alternative is you come up with an example of a group of homeomorphisms of a metrizable space where the smallest G invariant gauge structures are uncountable. And I think that would be interesting. But the other issue here is this condition that the orbit space be paracompact, which I need. And in fact, it's equivalent to this star refinement condition. So that lemma A says that not only does the G invariant, the orbit space being paracompact, not only does that allow me to do the proof, it allows me to star refine or find G invariant star refinements, but it's equivalent to that condition. So in a sense, this paracompactness hypothesis is in there because it allows me to do the proof, and that's exactly why it's in there. And so the question is, do you really need it? And I don't think you do, but and the reason is there are examples where the orbit space is not paracompact, but you can find isometrizable groups of homeomorphisms. Basically all you need to do is find an example where the orbit space is not paracompact. Well, if you take the countable ordinals with the order topology, that is not paracompact. And say you multiply it by Z2, and then you let the group, so you let the group act by just flipping the Z2 coordinates. Then there is an example where the group is equiregular and isometrizable. So there's a gauge structure on this space. Let's see. Well, this space, I mean, this space or the countable ordinals are completely regular. And so they're going to embed in some giant product. And that means that they have a gauge structure. And you can fool around and see that this group will be isometrizable, but the orbit space is not paracompact. So it's not hard to come up with examples that are outside of the theorem that I proved. And so I believe that there ought to be some theorem out there that applies in this more general setting, but I don't know what it is. And so, so I'm pointing out that this is because the orbit space is not paracompact, this group does not satisfy the star refinement property. In fact, you can come up with open covers of the countable ordinals that don't have star refinements. And so you can't use the approach that I took in these proofs to construct gauges, but it's still, what have I got here? So here's the conjecture that nonetheless, if you're in a completely regular space and you have a group of homeomorphisms that's equiregular, can you prove that the group is isometrizable? So this is, you get outside of the area where I can do a proof, and I don't know what the answer is, but here's a conjecture. I think that is the end of my slideshow. No? Huh? Oh, well, there's some example, but not interesting. But so that, on the other hand, I'd be, it's equally probable that this conjecture is false, that equiregular alone in this more general setting is not enough to come up with a G invariant gauge structure. So I don't know. Anyway, I'll stop there.
Any questions?
Yes, I have some questions. One thing that stuck out for me the whole seminar was that maybe the only definition that is not directly translatable from gauged spaces to uniformity spaces is equiregularity. Like every other properties that were used during this proofs of statements completely fit into spaces with uniform structure without referring to any particular gauge. And in most cases, you can use just a compact uniform structure. That's all you need. But this regularity condition is the only one that is not a large scale structure. It's more of a small scale structure in some sense, like Lipschitz condition, in a sense. And I thought maybe if we just try to avoid this Lipschitz condition, maybe replace it with something else that fits into category of uniform spaces better, then maybe we can get more clear results. It's just, I'll guess. But that's one thing I noticed.
I haven't thought about that, but I mean, it's an obvious question, I guess. So I don't really have anything helpful to say.
And like more generally, I kind of like to get rid of any metric per se components in such statements, because it's too strict of a structure on a logical space in a sense. And I would like to replace it with like a core structure, uniform structure in every place where I can. And I have a belief that most statements can be translated from gauges metrics to a combination of core structure and uniform structure. Maybe that would be possible in this case, but if you didn't thought about that, then I guess nothing I can say just directly after looking at that.
Yeah. Right. I don't know. I'm not really familiar with sort of coarse topology and so on. I'm not able to say anything right now about this, but I'd be, if you want to send me something.
I'm not
like link to a paper or something. I'd look into it.
I'm not like a specialist myself, and in general, this stuff is not very well written. Let's say there's a lot of space to make some cleaning in this area. So maybe sometime in a few years.
Okay. Thank you.
I'm sorry, Denis, where do you see core structure here?
Here it's not used anywhere, but like in general, whereas metric arguments can be broken down to coarse part and uniform part.
Okay, but here I understand what you say about the uniform spaces. It looks, yeah, it's a reasonable question if one can state theorems and state similar results in the domain of uniform spaces. But,
yes, and equiregularity is this strange condition.
Yeah, but for proportionals, I just don't see how it relates here. It is a different problem which might be not so related to this argument. But I don't know.
Yeah.
It would be interesting to know how essential this equiregularity to all of this. Like this whole theory of actions and fixed points.
Yeah.
Bounded space of bounded structures space.
I mean, to put this in the context of uniform spaces, you probably, you know, you can talk about uniform open covers in some sense. You know, if you have a uniformity, you must be able to relate some of these ideas to the uniformity, I would think. But
well, I think you what you are saying is already you don't need to change much. It seems.
Yeah.
Because so this you know how do you call them, the developments? They are well one way to define a uniform space is just by this collection of gauges, right?
Right.
And another is by these developments, and you basically explained why these two ways are equivalent.
Yes.
So it seems like uniform spaces are somehow. It should be possible to reformulate some of your arguments probably in this language of uniform spaces.
Yeah, I think uniform spaces are a special case, aren't they? They're not as general as the setting here, I think.
No, they are more general.
Yeah.
You can somewhat specialize to chronological spaces, and that will still be like not exactly in that scope of infinity gauge spaces, but in a sense not far from it. But uniform category encompasses all of things that said here. Maybe without some more fine properties, but it would be interesting to know which fine details will be dropped out.
Okay. Yeah, I have to think about it. But I think I agree with Sergey that they're very close. And so it's likely things are easily translatable. Hopefully.
I have a question. So this problem which you stated about non-separable metrizable spaces.
Yeah.
Yeah, I also recall that Sergey Antonyan also was very interested about some related problem. So for I guess for compact groups or locally compact groups, there is this G-invariant metrization theorem by Pelé. But it is for, if I remember correctly, it is for separable metrizable spaces. And it seems they cannot do it for non-separable case. And so he was very interested about that. But I actually don't understand the reason why it should be so interesting. I mean, separable metrizable spaces is something that you something that appears in practice, so to say, and for non-separable spaces, well, okay, but which what are good examples of non-separable spaces that you would be applying this to?
I didn't have any specific applications in mind. I just thought it's out there, you know, it's like Mount Everest. And it seems to me there's probably an interesting counterexample. Some space that's really big, a metrizable space, and a group of homeomorphisms where you just sort of locally, it's a metrizable space, and you can locally find metrics that are G invariant and capture the topology, but somehow you can't put them all together. It's just a problem that caught my interest. I don't have any application in mind. But, I just think if there is a counterexample would be as interesting as a proof. I'm not sure. I don't have anything very deep to say about it. I've thought about it and I can't build a counterexample at the moment. So I almost made, it's almost 2 hours. Yeah.
Any other questions?
Oh, you mentioned that you had some idea about the geometric proof of Bing-Moise metrization theorem. Can you tell something about your idea? Because I had similar idea a few years ago when I was somewhat interested in that. That was based on embedding a space into a product of Reeves complexes of various scales, but I didn't figure it out to the end, and I'm not sure if it works or not, but maybe if I can combine this idea with something of different origin that can make some interesting statement.
Well, I'm not sure. So you if I can find this thing.
You mentioned that you are interested in geometric proof of Bing-Moise theorem. Yeah.
Yeah, geometric proof of the Bing-Moe's theorem. Well, the inspiration for this is, if I can find the thing. I'm just trying to find the slide. That is too small for me to read. Keep going. Yeah. So. Right. So here, this was the statement, and I've read the paper Bing wrote about this, and as I said, it's a very technical.
Yeah, it's horrible.
Yeah, and so you're familiar with it, and I would like to find a proof where you embed the thing in some big Hilbert space and perturb it to make paths short. So, in the perturbed image.
Yeah, idea is clear, but how do you find
Right. Well,
something resembling this embedding?
I mean, I could tell you this. I had this idea listening to a talk a couple of years ago that I haven't been able to. Well, I haven't thought about it enough to really know that it works. But so my idea was this: that put it in a Lorentz space. In other words, it's a space where there are
semi-definite monospace.
I'm sorry.
You mean
a space where if things are horizontal, they're maximum length, and then as you tilt them toward slope 1, they get shorter. And
I understand.
Perturb this, take your original embedding in sort of the horizontal part and start putting tilted images in that shorten the diameter of things. And possibly you might be able to create an approximation to the original embedding with that consists of a sequence of tilted images where paths are shorter because they're closer to the light cone.
Oh,
something like that. I don't know.
Somewhat similar. My idea was that you want to take product of Rips complexes of your space.
What kind of? I'm sorry.
Rips complex. You just take points of the space and take a simplicial complex, where the simplex is a collection of points that all lie in a ball of small parameter. And you
you could map that in, right?
Yeah, and you metrize your Rips complexes, so the curvature of your simplices decrease along with the decreasing of size of your balls.
Yes.
And in a way, that is another model of your Lorentz space approach, but maybe slightly more geometric. And then there was a subtlety of some origin where you cannot really make a proper isotopy of your original naive embedding to the one you're interested in. And I think that problem may arise in your approach as well.
I didn't understand the problem that you said an isotopy is involved.
Yeah, because I think I don't want to make this without any writing. I don't have any means to write anything right now, so
yeah.
I'll stop.
Anyway, that was my one recent idea about how to do this, is somehow hope that there is a miracle that occurs if I think about this in a Lorentz space. Yeah, but I don't know.
Okay, thank you.
Yeah, you're welcome.
But where you are speaking about an isotopy, so isotopy of what embedding?
Oh, you have something like naive diagonal embedding in this product, and you want to isotope it to a good one, and why you want isotope and not just find the good, another one. This is because I want to then like maybe it's better for me to stop and maybe repeat it to you when we meet in person.
But could you remind which product do you mean?
I mean, you take a restricted product of this polyhedra. So, in a sense, you realize you can pact them as an inverse image of such polyhedra in a very peculiar way. And and then isotopy comes into play when you want to shade your big product into your inverse image in a suitable way. Maybe it makes some sense.
Do you mean Rip's complexes, or you mean maybe nerves of covers, of open covers? Which polyhedra?
I mean, you can make a peculiar inverse system of polyhedra based on this Rip's complexes that will converge to your compact, and then you want to compare this inverse system to the one obtained from like sorry, I'm a little bit at conveying some more technical details earlier. I'll just stop.
You know, I'm not sure what, are you saying Reese? Like R-I-E?
Reeves, Eliyahu Reeves, very good mathematician who mostly did things in metric geometry and geometric group theory.
Yeah, I'm not familiar with those, but I was thinking in terms of nerves of covers. In other words, you start out and you have a metric on the thing, so you can embed it in some big Hilbert space and isometrically, and then, but the metric, it's not one of these geodesic metrics, and there are possibly paths of infinite length in there. There are possibly points that are not joined by a path of finite length, and then you
in a sense, Rip complex is another way of thickening your space in a way that lies in it and retains, and it is geodesic embedded in some sense, but only in some sense, not literally.
Can you send me an email with just some reference to that?
Oh, you can just Google it. It's very common construction
So wait,
in geometry.
Is Reese R-I-E-S-Z in English? Is that
R-E-P-S.
R-E-C-S?
R-Y-P-S. Sorry, R-Y-P-S.
Okay, I'm not, yeah, okay.
I wrote it in the chat. Yeah.
Oh, Rips. Oh,
Rips.
Is this the Israeli?
He's like Jewish.
Yeah.
Born in Soviet Union.
I don't know where he was born. I think I met him in Israel. But yeah, I know what Rips complexes are. Yeah. Right. Maybe there's a useful idea there. But, I don't know. But what I was thinking was I wasn't thinking of trying to find an isotopy. I was just going to take a sequence of embeddings where they were tilted more and more and things got shorter, and then you embed in some countable product, you use all of them to find a new embedding.
My idea is that using a sequence of isotopies makes the result converges to an embedding. That was a spiel of my initial idea, but didn't work quite yet.
Okay. Okay. Well, another good idea. Think about it. Yeah. Okay. I should say that I don't think of myself as a general topologist, but this theorem is clearly in that world. And, as I said, somebody could have proved it back in the era of A.H. Stone and Ernest Michael.
Yeah. Unfortunately, I think there are no general topologists here, or no people who are entirely into general topology, at least.
Yeah, right.
Yeah,
Well, they're hard to find. I think they're hard to find.
Well, they have a seminar at Moscow State University. So, Alexander seminar, right, Oля?
Oh, they do. Yeah.
Maybe it's good that they
Right,
keep
right.
it to themselves.
Yeah. Well, in the U.S., there's always there's one conference every year where they there's always sections of general topology. It's this spring topology conference that they hold. I think it's already taken place this year, but I didn't try to, or maybe it was always a Zoom conference. I'm not sure. That's the outlet for general topology in the US. Yeah. Okay.
Are there more questions?
So can I ask you a question? Is it before COVID, was your seminar an in-person seminar?
Yes.
And have you gotten back to that at all?
Well, partially. Partially. So there were some offline talks. I think in February, in March, in April, we had some. And even in September, we also had a few. Yeah. So well, so we are. It's a combination. We have a offline talk, but with Zoom. And then many people connect by Zoom and don't come to the room.
Yeah.
So,
right. So are they usually in Russian, the talks?
mostly, but sometimes in English.
Yeah, because I was looking at the list of talks. Some of them look quite interesting.
Well, some of them are in English, and I think so. If you look at the English version of the seminar webpage, they are. I tried to mark them, talk in English, so they should have videos in English available. Not so many of them, but they exist.
Yeah. Okay.
I had a question about our project, but that could be separate. So we should stop the seminar first.
Okay, I'll stay on.
Yeah. So if there are no other questions, then maybe we could finish. Yeah. So then goodbye, everybody.
Thank you.
Thank you for joining us. And thank you, Reed, for the wonderful talk. It was very interesting.
Good. Thank you.
Thanks for inviting me. I didn't know how to prove these things, and now I understand.
Yeah.
I mean, for compact groups, which is Pellé's theorem, I didn't know how to prove it, but now I understand.
Yeah. Well, he may have a simpler proof. I didn't read his proof.
Well, your approach is simple enough. I was thinking about this in connection with the Hilbert-Smith problem, but that seems to require only compact groups. So I don't know, but probably. Yeah, all right. So I'll stop the recording.
Yeah,
And
thank you for your questions.
thank you for speaking.